complex number is a number of the form x plus y times I, where I, which is actually the Greek letter iota, but we will just call it I, is the square root of minus 1. This means that if we take iota or I and square it, we will get minus 1. If we have the square root of some number and we square that, we just get rid of the square root sign and we have what's inside the square root sign. The numbers x and y here are real numbers. So if you think about it, there are no two equal real numbers that multiply to give minus 1. You know that if we multiply minus 1 by plus 1, we get minus 1. If we multiply minus 1 by minus 1, we get plus 1. So these two numbers are the same, but they multiply to give plus 1. Of course, if we multiply plus 1 by plus 1, we get plus 1. But no two numbers the same give minus 1. So we just pretend that there is such a number. We can think of it as an imaginary number. The imaginary number I. So this here is I. We just call it I. And this is also I. I times I is just I squared. So we just invent a new number. So historically, there was a need to invent this new type of number when mathematicians were studying the solutions of certain polynomial equations, cubic equations, quadratic equations, and so on. Here is an example of a complex number. It's got the form x plus yi. X and y are real numbers. Here x is 3, y is 4. Both of these numbers are real numbers. So this is one complex number. It's made up of two parts. This part here is actually called the real part. It's written RE for short. And this part here, the coefficient of I, is called the imaginary part. This is written IM for short. Here's another example. Here x is minus 7, y is 11 over 13. Both of these numbers are real numbers. Here x is the square root of 2 and y is minus 6. The square root of 2 is a real number. It cannot be written as a fraction. It's not a rational number. We can't write it as a ratio. It's referred to as an irrational number, but it's still part of the set of real numbers. The number 5 is actually considered to be a complex number, because we can write 5 in the form 5 plus 0 times I. 0 times I is actually 0. So we just get 5 plus 0, which is just 5. So you see that this here has the form x plus yi, where x is 5, y is 0. Both of these numbers are real numbers. The number I itself is a complex number because we can write it as 0 plus I. If you like, you can put a 1 here. X is 0, y is 1. Similarly, we have the complex number minus 3/4 I. We can write that as 0 minus 3/4 I. So in this example, the real part is 0 and the imaginary part is minus 3/4. Now I want to mention the number system and how complex numbers are a part of the number system. The most basic type of number or numbers are the counting numbers. They're denoted by the letter n, n for natural numbers. So those are all the positive integers. So 1, 2, 3, 4, 5, 6, 7, etc. Sometimes 0 is included in this set, and sometimes it's not. I'm going to include 0 in it. Now, the set of natural numbers, denoted by the letter n, is a subset of a larger set, which includes negative integers. So I have shown 3 elements in this set. They're the elements minus 1, minus 2, and minus 3. So you can see that z includes negative integers, but it also includes n. So you could say that n is a subset of z. You can use this symbol here for subset. These sets in turn are subsets of a larger set denoted by the letter q. Q stands for the set of rational numbers, that is, numbers that can be written as ratios of integers. So for example, a half is the ratio of the integers 1 and 2. It's 1 over 2. You can see that it doesn't belong in set z because it's not an integer. Similarly, minus 11 over 12 is a rational number. It's the integer minus 11 divided by the integer plus 12. Similarly, 101 over 203 is a rational number. It's the integer plus 101 divided by the integer plus 203. Of course, integers can be written as rational numbers. The number 3 can be written as 3 over 1, an integer over an integer. So you can see that the number 3 is an element of set Q. Similarly, a number like minus 2 can be written as minus 2 over 1. So it's a rational number, so it's an element of the set Q. So basically n is a subset of z, and z in turn is a subset of Q. Now there are numbers that cannot be written as the ratio of two integers. They're the so-called irrational numbers. For example, the square root of 2 cannot be written as some integer, we call it a, divided by another integer b. It's impossible. Another example is pi. These are the so-called irrational numbers. They can't be written as a ratio. So they belong outside of Q. They're not elements here. They can't be written as a ratio of integers, so we have to show them outside. These numbers form part of a bigger set called a set of real numbers. So the real numbers includes Q, Z, N, and numbers that are irrational, like pi. Actually, all the square roots of non-square integers are irrational numbers. As a matter of fact, there are more irrational numbers than rational numbers. Remember, pi itself cannot be written as a rational number. Pi is not equal to 22 over 7. 22 over 7 is an approximation for pi. You cannot write pi as an integer divided by an integer. It's an irrational number. Finally, we have numbers that are complex numbers. A number like 3 plus 4i, where I is the square root of minus 1. Now, that's not a real number. It's made up of two parts, but it's a single number. This dot represents it. Its real part is 3. This is actually called its real part, and its imaginary part is 4. So we need to show that outside the set of real numbers as part of a bigger set called the set C of complex numbers. So the most basic complex number really is the square root of minus 1. All complex numbers, all non-real numbers, are built up from the square root of minus 1. The square root of minus 1 is just I. It's denoted by the Greek letter iota, or I. So any number of the form x plus yi is a complex number. Now, it belongs out here if y is not equal to 0. So it's assumed here that y is not 0. So, well, if y was 0, then we would have just a real number x. So we wouldn't show it out here. We would show it inside the set R. It would be in here somewhere, depending on whether it's irrational, rational, a negative integer, or a positive integer. We'd show it somewhere inside the set R. But I'm assuming here that y is not equal to 0. So any number of the form x plus yi is a complex number that's not real. Now I want to look at the addition and subtraction of complex numbers. Suppose we have these two complex numbers, 3 plus 4i and 7 plus 9i. So this is all one complex number. Its real part is 3, its imaginary part is 4. This is another complex number, its real part is 7, its imaginary part is 9. I put brackets around them like this, but you don't actually have to put in those brackets. The way we add these complex numbers, the way addition is defined for complex numbers, and the way that makes sense when complex numbers are applied to solving polynomial equations like quadratic equations, for example, is to add the real parts together and add the imaginary parts together. So we have 3 plus 7 is 10, 4 plus 9 is 13i. If we want to do subtraction, we just do it like in ordinary algebra. We can write out all of this. I can just drop the brackets here because this is not multiplied by anything. This is just 3 plus 4i. I can take the minus sign in here. Minus 7 minus 9i. It's like multiplying minus 1 into this expression. And then gather up like terms. We've plus 3 minus 7 is minus 4. So the plus 3 and minus 7 are like terms. The plus 4i minus 9i are like terms. They can be gathered together. Plus 4 minus 9 is minus 5, so we get minus 5i. It's just like ordinary algebra. So the complex number 3 plus 4i minus the complex number 7 plus 9i is the complex number minus 4 minus 5i. Suppose we want to multiply the real number 5 by the complex number 3 plus 4i. Well, actually, I said 5 is a real number, but as I explained earlier, 5 is a complex number because 5 can be written as 5 plus 0i. It's a real number, but it's a subset of the complex number, so technically it's a complex number whose imaginary part is 0. Anyway, to do this multiplication, we just do it like in ordinary algebra. We just take this 5 and multiply it inside here. So we have 5 times 3 is 15. When we multiply 5 by 4i, we get 20i. So we get the complex number 15 plus 20i. Suppose we want to multiply the complex number 5i by 3 minus 7i. So the 3 minus 7i is a complex number. It's made up of these two parts, so I put it in brackets. You don't have to put 5i in brackets because the real part of the complex number 5i is actually 0. We could write it like this, 0 plus 5i, but we don't need to do that because of that 0, so we just have this single term, so we can leave off the bracket. So we just multiply like in ordinary algebra. We multiply the 5i by the 3, which gives 15i, and we multiply 5i by minus 7i. Now what will that give us? It's similar to multiplying 5x by minus 7x. We get 5 times minus 7 is minus 35. X times x is x squared. It's the same idea here. We have 5i times minus 7i gives us minus 35. I times I is written I squared, of course. Now, however, there is one difference in handling this expression to what we have if we're just say multiplying 5x by minus 7x to give minus 35x squared. Because since I is the square root of minus 1, I squared is minus 1. So we just replace this I squared with minus 1. So what we have is minus 35 times minus 1 is plus 35. So I'll write the real number 35 first, and I'll write this part second. You know, just to get it into the standard form of a complex number. So this is just all one complex number. The real part is written first. That comes from multiplying minus 35 by minus 1. And the imaginary part is written second. The imaginary part is actually the coefficient of iota, which is 15. Now, suppose we want to multiply the complex number minus 2 plus 3i by the complex number 5 plus 4i. This complex number has a real part that's not 0, so we need brackets around it. This is made up of these two terms. And we bracket this one here. So this is just like ordinary algebra. We take the first term here and just multiply it into all of this here, and then we take the second term and just multiply it through here. So we'll end up with 1, 2, 3, 4 terms. So minus 2 by 5 is minus 10. Minus 2 by plus 4i is minus 8i. Plus 3i by 5 is plus 15i. Plus 3i times plus 4i is plus 12i squared. And of course I squared is minus 1, so we replace this I squared with minus 1. So we have plus 12 times minus 1. That will give us minus 12. Then we gather up like terms. Minus 10 minus 12 are put together to give minus 22. Minus 8i plus 15i is plus 7i. So we get this complex number here, minus 22 plus 7i. The next thing I want to consider is powers of I. Well, we know that I squared is minus 1. Suppose we want to get I cubed. Well, I cubed means I times I times I. When you cube a number, you just multiply it by itself twice. For example, 2 cubed would be 2 times 2 times 2. So let's see what I cubed is. Well, we could also write this as just I times I squared. When we multiply these two i's, we get I squared. And we end up getting I times I squared. I squared is minus 1. So we have I times minus 1, which is minus I. So we see that I cubed is minus I. Now what about I to the power of 4? Well, we could write I to the power of 4 as I times I times I times I, or we could write it as I squared times I squared. See, if you add these powers, 2 plus 2 gives us 4. And we know that I squared is minus 1, so this is just the same as minus 1 times minus 1, which is plus 1. So I to the power of 4 is plus 1. What about I to the power of 5? Well, we can write I to the power of 5 as I to the power of 4 times I to the power of 1. You can put a 1 here if you like. I to the power of 1 is just I. You just add the powers, 4 and 1 is 5. It's just like x to the power of 5 equals x to the power of 4 times x to the power of 1. It's just like dealing with powers or exponents in basic algebra. But we know what I to the power of 4 is. We already worked it out up here. We know that it's equal to 1. So we have 1 times I to the power of 1, or 1 times I, which is just I. So we know that I to the power of 5 is I. Now let's suppose we want to do something more complicated, like get I to the power of 97. Well, we could write this as I to the power of 96 times I to the power of 1. We could factorize it like that, because 96 plus 1 is 97. We can then go on and write I to the power of 96 as I squared times I squared times I squared times I squared 48 times. Because 2 times 48 is 96. So we can break I to the power of 96 down into these 48 terms. Each term is just I squared. So, if we want to multiply this out, we just have 2 plus 2 plus 2, 48 times. That would give us 96. But each of these I squareds is minus 1. So what we actually have is 48 minus 1's multiplied together. The whole lot of this is times I to the power of 1 or just I. Now, what's 48 minus 1's? Well, we could also write this as minus 1 to the power of 48. Since this number is an even number, we get plus 1. If we multiply minus 1 by itself so that we have an even number of minus 1's, 48 is an even number, we get plus 1. See, because if we can group them into 2's, this is plus 1, and the next pair is another plus 1. And in total we will have 24 of these pairs. 48 divided by 2 is 24. So what we end up getting is plus 1 times I. But plus 1 times I can be just written as I. So now we know that I to the power of 97 is I. What I've done here is to write down successive powers of I in this row, and what it is above in this row up here. So you can see I squared is minus 1, of course. I cubed is minus I, that's what we had already. I to the 4 is 1. I to the 5 is actually I. I to the 6 is minus 1. So now you can see we're starting again. So the sequence starts again. So it goes from minus 1 up to plus I, and then it starts at minus 1, and it'll keep going. The next term here will have to be plus I, and then after plus I we have minus 1, so we know that I to the power of 10 must equal minus 1, and so on. So basically these are the 4 that get repeated. So when we raise I to a power, we always get one of these 4 numbers.